Mm.
Let's see.
Yes. Is there?
Maybe there's a.
Yeah, you can look into something.
Well, this is not like the
Oh.
place.
See.
Maybe it's the. Are you there?
What is this? This is connected to. Connect the cable to your device. But I think you want to connect this to the device. I think that's-
I think at this point, maybe.
Yeah, I guess. Okay. Wait, give me a second. Can you start the lecture real quick?
I don't suppose anyone with an experience with using
Not streaming, right?
Hmm?
You said-
maybe
Yeah.
your experience which shows up as
Oh,
using
is that not an instrument?
music.
Hmm.
Oh, well, there's a video left now. Maybe we should try.
Please enter the meeting passcode followed by the pound sign.
Hmm.
You are recording in progress.
Hello? Hello? Solid. Okay. Now let's share the screen. Okay, here we go. Sorry about that, everyone. Hopefully this will work now. Yeah, welcome to week 2 of the Stanford AI Club's PyTorch class. For those of you who weren't here last week, we basically went over just some of the basics of deep learning and some of the intuitions behind why deep learning might be useful for solving a lot of problems. This week, we're going to be just doing a high-level overview of the entire deep learning pipeline, and in the next few weeks, we're going to go into each one of the steps individually. Okay, yeah, so first, we're just going to do a quick overview into installing PyTorch. However, we aren't actually going to use that today. We're going to be using Colab, which already has PyTorch installed, which is very nice, and it prevents a lot of headaches. So first, what is PyTorch? PyTorch is kind of a Pythonic user-friendly machine learning library. So it's kind of, so a lot of people think it's sort of like NumPy. However, it really builds a lot of things on top of that. So you can kind of think of it as like NumPy, but with the ability to automatically compute gradients with respect to matrix operations and things like that. But then on top of that, it also has a lot of very useful library implementations for a lot of things you might use in deep learning, such as optimizers, activation functions, various network architectures, things like that. So first, I'm just going to briefly go through this, and then we'll share the slide with you, so you can follow this in your own time. Normally, the first step you do when you're starting a project is to create some sort of environment. I personally prefer Conda to create my environments, but you can also do virtual environments. You can also, here are a couple of ways you can install requirements for a file. Oftentimes, if you're working with other people, it's a good practice to just create a requirements file or environment file, depending on whether you're using Pip or Conda, to store the specific requirements that you're using so other people can reproduce your results. And then for installing PyTorch, they have on their website, they have this very, very nice, just kind of like command builder that for most situations, you just click on your specific use case and it will generate a command you can run them to install the correct versions of things. So here, your OS, if you're using a remote server, so if you're like SSH or something, it's almost certainly going to be Linux that you're using. And then you can use your package manager of choice. And then this is kind of important, is what version of CUDA you're going to use. So CUDA is just like an API that I think NVIDIA makes that lets you just interact with their GPUs. And so there are various versions of that which will get better over time. And so you want to make sure you install PyTorch that's compatible with the right version of that. And so one thing you can do is if you know you have NVIDIA GPUs on your system, you can run the command NVIDIA-SMI. And it will output all this information, and in the upper right, it will tell you the CUDA version. Are there any questions about that so far? Solid. Okay. So a lot of the stuff we're going to go through today is also happening in parallel on this Google Colab. So feel free to either go to that link or use that QR code. Is the link working for everyone? Does anyone have any troubles opening the link? You can also just work with the neighbor. If you need to, like also put it in fine. Oh, nothing. Yeah. You're just making sure you can open the link. All right. Moving on. Okay, so one of the nice things about Colab is that Google will give you some free access to GPUs. It is somewhat limited, and you can only use them for a certain amount of time every day or week or so. But it's still nice to just play around with things, test things out. So if you click on this little like downward facing triangle in the upper right hand corner, if you click on that and then click on change runtime type, you can switch to, I recommend using T4 GPU. And then click save, and then it will restart the notebook, but you'll have access to GPUs. Additionally, if you click the little RAM disk button just to the left of that drop down, you can see all of the like resources you're using. So how much RAM you're using, how much of the GPU RAM you're using, and how much of the disk space you're using.
I have a question. Like I've heard about like TPUs, but what is actually the difference between GPUs?
It's a pretty subtle difference. For our purposes, they're basically the same thing. TPUs are, I think, specifically Google's like accelerated compute system. That are like they're designed more specifically for deep learning.
But they are actually like they are more efficient or like just no.
It really they're a lot better than some GPUs. They're also a lot worse than other GPUs. It really depends how much money you're spending on GPUs. Yeah, I think that this stands for like tensor processing unit, and so it's like specifically working with like high dimensional tensors. Yeah, whereas GPUs, I mean, it's just like left over from originally GPUs were mostly used for like graphics, but now they're continually being used for deep learning.
And one thing I'll add is that in practice, I use GPUs much more often than GPUs.
Oh, you will.
I know.
Yeah. Do you want to go watch the face stuff?
Yes. Wait, when's the data coming up?
You have a bit of time.
Yeah.
Yeah. Okay. So what is the standard pipeline in deep learning? Okay, there are, I mean, you can argue for different or more or less steps, but this is what I decided to go with. There's about 5 different steps. So first is the data. The data is arguably the most important part. You have to get your data, prepare it, and you have to make sure it's in the right format such that you can efficiently use it to train a model. Then you actually have to figure out what model you're going to use, how you're going to create it, how that's going to work, what its internals are going to be. Then you can train your model. So that you'll have a loop that just continually tries to improve the model, make it better and better. And then the evaluate step is sometimes done in parallel with the training, just to see how the model is improving over time. But also, once you finish training the model, you'll often run a full suite of tests after to see how good it actually is. And then depending on what you're doing, so especially if you're working in like a production pipeline at a company or something, you probably want to save the model and to be able to load and reuse in the future. And research is also useful, just so if you need to reproduce the results or you want to share your work with other people. It's generally good practice to save the model so you don't have to go training it all over again. Okay, so I don't know how much experience you guys have with machine learning pipelines or just like creating like some sort of like work pipeline in general, but does anyone have any ideas for what the benefits might be? Yeah. Efficiency is good. Anything else? I mean, no worries. I mean, you're taking this class to kind of learn about this. Yeah, so here are a few of the things that I wrote down. So first, modularization. You kind of are able to break down this really complex problem into a bunch of much simpler, more manageable steps. Additionally, this allows for better reproducibility and collaboration with other people. You can work on one part of the pipeline where someone else works on the other, and you don't have to worry about them getting all messed up and convoluted. And this also, yeah, increases efficiency, especially if you're collaborating with people and how quickly you're able to iterate and build new models. It also allows you to scale up a lot more very easily because you can just like scale up specific parts of the pipeline very easily and you don't have to worry about the other parts. And yeah, it allows for quick experimentation and then deployment at the end.
Yes. So now let's get started on the first aspect of the pipeline, which is the data aspect. And the main overarching theme in data is how can we sort of take some amount of data, structured or unstructured, and get it into a form where we can start feeding it into a neural network and actually getting it to start learning. So, why is data important? So the data is fundamental to the performance of a neural network. And often, if you see this like really good models, like really good large language models, for example, the secret to them being really good is, of course, a training aspect, but oftentimes the data. And having really good, high quality training data, sort of combined with a really good data pipeline can make neural networks perform a lot better. And PyTorch, luckily, has many useful APIs to sort of abstract away this process of massaging your data to get it into a form that a neural network can start learning. And in this lecture, we'll be covering some broad, big picture things that can help with this. So many big picture APIs in PyTorch. So fundamental things to know here for data. First, how can you load data into a structured format in PyTorch? Second, how can you transform this data to fit your needs and help get the neural network to start learning? And third, and we won't cover this in this lecture, but we'll cover this in a future lecture, is how can we start to think about different types of data, images and audio? How can you transform those? And we'll talk about this more in the later lecture. So I guess in terms of how we'll be teaching this, most of these slides will just basically be code segments, and I'll walk you through them. And the reason I decided to do this is that oftentimes a lot of data work is very practical. And I think seeing exactly what the implementation is helps a lot. So the first thing I'd like to teach is the dataset class. This is a fundamental thing in PyTorch. So the dataset class is just an abstract class used to represent some custom dataset. So you have some dataset, and then you can sort of packages it in this dataset class, and then you can start leveraging a lot of APIs that PyTorch has to make stuff a lot easier. So a dataset class needs 3 methods to get implemented. To initialize it, you need a method to sort of compute the length of the dataset, and then a method so you can get the ith sample in a dataset. Okay, so in this init method, you can oftentimes see stuff like the image path where the data is actually located, things like that. Len is just again the length, and this is get item is just a method to get the data point at index IDX, right? So oftentimes in this get item, you'll sort of want to do some kind of transformations, and then you'll get this data at point I. And now this might seem a little bit confusing now, but we'll go into a concrete example just now.
Also, one more thing, I think there's a small type of data should be 2 double underscores for the numbers for after get item as well.
This is correct. Yes. Yes. So now let's go through example. And here we have, let's say we have some image data set. So again, we won't be covering how we can actually do transformation for image data set, but I wanted to give an example. So in the init here, you have the directory to the root. Okay. The root directory. So this is where all the images actually are. You have the directory to the image paths, and you have a directory to the transform function. And what is the transform function? It's a function that sort of takes in some images and transforms it in a form that a neural network can start learning. And we'll go get into sort of some functions that can do that in a few seconds. So that's in it. Now we have the length. Length is again, we take this image path and we just give the length of it. Okay, cool. And as you can see, image path here is just, I believe, just normal, like normal listing. Okay, so we can take the length of it using the length. Now get item. So get item here, again, remember we have a self and the IDX. So the point here is we want to get the ith sample, okay, in this image path. What we do is we open it, so we get the image name in position IDX. We then take the image and actually open it. And then if we have a transform, we apply this transform function, so this is a callable, to this image, and then we return the image, and we get the item at position IDX. So this is sort of a standard example of sort of a real world case of the dataset class. Let's move on to the next one. Yeah. So now, what is self-transform? This might be confusing with that. And what this is basically, again, like I said, this function you can take, in this case, image, do some sort of processing to it, so you can get it into another image that you can actually start feeding into the neural network. And in this lecture, we won't be talking about images or audios or any other modalities, how we can do transformations, but we'll focus on the case where, say, you have like 20 columns of like numbers and like and say another column of just numbers. We won't be focusing on images and audios. We'll do that in another lecture, where we actually go, I think the next lecture actually, where we go into the data pipeline. So the first thing, normalization. So the normalization here, the goal here is to adjust the data to ensure that each feature contributes sort of equally to the model's predictions. And the idea here is that oftentimes, say you have 3 features. One feature is super high in scale, like 1 million or something. And then so 2 other features are like 0.5 and like 0.8. And often what you have in the machine learning model is that just because this feature is super high in magnitude, that the machine learning model will prioritize that feature versus the other features, which might be more important, but are simply smaller in like sheer magnitude. And you don't want that to happen. And so use normalization. And the goal here here is to help the neural network learn and to help ensure more stable convergence. And like we said before, ensures that one feature isn't too important in the model's prediction, is just by the sheer magnitude of it. And one such technique to do this is called Z-score normalization, where we have some data set and we will transform it into a data set with 0 mean and unit variance. And again, this is something you probably learned in like a stats class. So now we'll sort of show how you can do the Z-score normalization in the dataset class that we had before. So remember dataset class, you go back here, you need to initialize it, length, get item. Okay, so initialize it. So you have, in this case, we have our data, whatever data is. We put that in the sub.data. We also compute the mean and the standard deviation using some numpy. Okay, so now we have sub.data, sub.mean, sub.data deviation. I don't have the length method because again, the length is just the length of the sub.data, so I don't have that here. But you will need that if you actually implement it. And lastly, you have this get item. And what all we do in get item is we're standardizing the data using this Z-score normalization, which we take this data at position index, we subtract it from the mean and divide it from the standard deviation, and from that we get the standardized data so it's sort of now it's sort of distribution with 0 mean and mean. And finally, we return this. And I think one thing that's interesting here is that you don't just return the standardized data. We return the standardized data in tensor format, right? As a PyTorch tensor. And the reason is that in get item, I believe, all the output, the return must be a PyTorch tensor. So it can be, say, a NumPy array or something. So in this case, this is a NumPy array, and sort of convert this to a PyTorch tensor using this torch.tensor. And before I go on, does anyone have any questions? Or what you have to go? I think some people might. Question? Oh, another way is min-max scaling, you sort of scale it between the max and the min. Again, it's sort of similar to you, instead of storing the mean and the standard deviation, you just store the min and the max value. You do the same thing, you just take the data acquisition index, you subtract it from the min, and then you divide it from the max and the min. So this is just another way of doing it. Cool. So now the data loader class. So far, here we talked about is the data set class. But oftentimes in a neural network, and Kai will talk about this in, I think, a few slides, is that we don't typically train on one data point at a time. Okay? You don't train on one data point at a time. Instead, you train on batches of data, like say 10 or 20 data points. And we'll talk about why. I will talk about that in, I think, like 10 slides. Okay? And another thing is when dealing with large data sets, it's very impractical to sort of load all the data at once. And large data sets are super common in neural networks. And again, for example, there's this paper from Meta. They released their new language model called Llama 3. And that was trained on around 15 trillion words. And that's a lot, right? Around 15 trillion words is a lot of text. And you can't simply load that in all at once, okay? And unfortunately, the sort of dealing with these large data sets and dealing with these batches of data isn't something that is natively provided by the dataset class. So what do? Luckily, PyTorch has the data loader class, which sort of takes care of this batching, takes care of loading these large data sets, and so forth. And so let's now go into that. And we typically use this data loader class in real world applications.
I have a question, but like,
Yes.
so how important is it, for scaling data if you are working with like a large model? Like, I understand when you have like pre-processed, like to remove noises, but like otherwise, I think the model it's just like a linear transformation divided by the sampling. So like, should the model like learn by itself how to like rescale?
So the model definitely can. It's however, it makes its job harder. Especially because a lot of the default like ways to initialize the weights of the network and a lot of the activation functions are designed specifically around to work really well with data sets that are kind of normalized as well.
Yes. But again, like Kai said, if it's like a large enough neural network and you train it enough times, you probably don't do that. But it does help a lot, especially with like smaller data sets or like smaller models.
The other thing is if you just have like a linear like transformation, if you then compute the gradients with respect to really large inputs, the gradients will end up being
Cool. Let's move on. So data loader class. So what are the the parameters of the constructor for the data loader class? Okay. So first is the data set. And that is the only thing you sort of need. That's only like necessary parameter, data set. Okay. So data set is the data set from which you would load from. And importantly, this is a data set object. So remember the data set object class we talked about before, right? So it's that. Okay, that is the data set. Okay, and this is mandatory. Okay, cool. But like we said, data loader allows many other stuff like loading data in quickly and having batches, right? And there are other parameters which help with that. So first is batch size. So that is the number of samples in each batch. Okay, so I think it defaults to 1, but you can like make it 20 or however much. And I think I will be talking about the pros and cons of having bigger and smaller data batches. Next is this parameter called shuffle. So data loader, it sort of natively supports shuffling, and it's a Boolean true false, indicating whether the data set should be shuffled or not at the beginning of something called epic, which is sort of one run through all the training. Okay, so before that, you want to see, okay, are we going to be shuffling the data or not? Next, we have this thing called the collate function. So what is the collate function? The collate function is something that's sort of used to take each data sample and merging them together when having our batches. So you can, and so the collate functions, sort of a function, you have all these individual data points and you can sort of merge them together. And there's a function to tell you how you can merge all of these samples together to form the batch. And there is a default collate function, and generally, you probably want to use that. But I will say for like very specific especially like real world cases, you will oftentimes want to actually modify this function as well in certain cases. So that's why I put this, and there's also many other things in this method, in this function as well. There's like the number of workers, there's like this option to like pin memory. There's also like this option called drop last and stuff like that. I can talk more about this. So I will talk more about this in next lecture actually, where we sort of go into more optimizations of the data loader class. So an example is this. So first we have some data. So this is just a sample data. So let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, or whatever. Okay, as your data. Now what you have, let's say you have some my dataset class, right? This is the dataset class from before. Okay, so now you have dataset equals my dataset, and then you sort of pass in the data here. Okay, and this is dataset. This is again the same dataset object that we had before. Remember the 3 methods, like remember length, get item, init. That's that. Cool. So now we have that dataset, and now we pass that into data loader. So data loader, we pass in the dataset. We say we have batch size equal to 2, and then we also pass it a collate function. So in this case, let's use a custom collate function, although you probably don't need it for this. The collate function, you have this, and what do you do here? So here you have the input as a batch, right? The batch of size 2, and then you just sort of just stack them together. Okay, and that will be your collate function. And now, I think one thing that's important to note is that the data loader is something called an iterable, right? So what iterable sort of is that you can sort of iterate through it in a for loop, for example. Okay, so now if you do for batch in data loader, and then you print the batch, you will see that the first, so remember the batch size is 2, and there's 3 data points. Okay, so first you get the first 2 examples in the first batch. So 1, 2, 3, 4, 5, 6 in the first batch. And the second batch is, yes, perfect. The second batch is 7, 8, 9. Okay, and remember, this is not complete. Okay, there is 3, so there's like 1 sort of like not a full batch. And there is an option in PyTorch, in this data loader class, to just remove the last batch if there isn't enough examples. So you can do that as well. Again, like I said, almost unlimited customizability. So any questions before we move on to modeling? And like I said, we'll talk more about data in the next section.
We only have about 20, 25 more minutes, so this will be a bit quicker. Okay, so first, I'm going to talk about modules. So PyTorch modules are really the building blocks of neural networks. If you remember last week, we talked about layers and how deep learning is composed of a lot of layers. This is kind of analogous to that. So often you will build like layers and sometimes custom layers, use built-in layers. And those are implemented as modules, and you can also combine them together to make more complicated layers. And the nice thing about modules is they abstract away a lot of the tedious stuff about deep learning. So it'll basically allows you to automatically compute gradients and update parameters and sample those models and transfer things to GPUs and things like that. That otherwise would be kind of tedious and annoying to do by hand. So just some of the common modules that are built into PyTorch directly, they're found in torch.nn, things for neural network. So we saw last week already linear layer. This is implemented as a module. There's also some other common ones such as convolutional layers. You also have activation functions like ReLU, and also sometimes even complete architectures like the transform. So yeah, we saw this example last week with the linear or sometimes called dense layer. It's fairly straightforward. Basically, just apply a linear transformation to the input. Due to time, I'm going to skip the details unless anyone has any questions about this specifically. Okay. And so we can look at the internals of this, and we can see that, okay, if we create a linear layer where it has 3 input dimensions and 4 output dimensions, we can actually get the matrices A and the vector B through the dot weight and dot bias parameters. And you can see that, yeah, we end up with a 3x4 matrix and a 4 vector. Additionally, you have some common activation functions. So you have the ray loop, which is just a straight line with a kink at 0. You saw a sigmoid, which is the orange one, that kind of interpolates immediately between 0 and 1. And then a more modern one, which is J loop, which is kind of like it's a smoothed out ray loop, and that sometimes helps with certain issues with the non-differentiability of 0 function. So as I said, deep learning is not just one layer, you're stacking a whole bunch of them together. And PyTorch has a very easy way or built-in way of doing that. And that's the sequential module. And all it is it takes in a list of submodules, and then it just passes the input to the first one, and then takes that output, passes it to the second one, and so on and so on. It just applies each of the modules sequentially, and it's just a really nice wrapper. So you don't have to do this at the bottom where you define one, define an X, define another, and then manually pass them all into each other. Yeah, so are there any questions about that? We're going to go more into modules in a couple of weeks and defining your own custom ones as well. Also, I mean, I don't know if you've been following along on the Google Colab, but if you have, and you run into those things, there's some more interesting things about that. There's also an example of a convolutional neural network or a convolutional layer and applying that to an image and seeing what that looks like. Okay, so the training loop. Last week, we explored gradient descent and kind of an intuition of why that works very well, where we have this loss landscape on the right, and we want to try and move in a direction that minimizes the loss. And a very easy way to do that, and a very computationally efficient way to do that, people discovered, is to compute the gradients with respect to all the methods, and then move in the opposite direction. And that tends to decrease the loss. So just an overview, stochastic gradient descent, we compute the gradient of some objective thing that we're trying to minimize with respect to every single parameter in the model. And then we perturb those parameters a little bit in a direction that decreases the loss for the objective, and then we repeat many, many, many times. And how do we actually do that in practice, though? Because the toy example we were showing before with the linear layer is really easy to get the gradients by hand. But these networks get really, really complicated really fast, and you don't want to have to do that. So luckily, PyTorch has some built-in functionality to automatically compute the gradients for you. And the real trick is to decompose all of these operations, all of these modules, all these layers into much simpler operators. And then we can compute the gradient, or we can compute the gradient of each of those operators very easily. And then the real trick, or the real technique that we use, is then use the chain rule very, very, very deliberately to then start at the output, and then we work our way backwards using the chain rule to then compute the gradients of early and earlier parameters in the network. One question you might be having is, well, why do we have to compute the inputs first? So this is called the forward pass. And the reason we have the forward pass is because gradients are a function of the input to each operation. And so we need to actually store those inputs in order to compute the gradient. And so what we do is we first compute all the way through, that we take the inputs to the model and we get the output and compute the loss. And then we can work our way backwards, so we're building up the gradients that way. And so these are called the forward and backward passes. Are there any questions about that? So, okay. So what does one training step look like in PyTorch? So what your training loop will generally look like, or what one training step will generally look like, is you pass in some input X to a model and compute some predictions or output. And then from there, you then compute some loss function. And usually that's related to some like round trip y. And then in PyTorch, all you have to do to compute the gradients is just take that loss term and call dot backward on it. And that will compute the gradients for all the parameters that went into and all of the functions that went to actually producing that output. And then we can update the parameters using some optimizer. And we'll get more into optimizers later lecture. So what we are currently doing is gradient descent, but there's some more complicated ones that tend to work better. And then you have to call optimizer.zerograd. And this is just to clean up and reset some things. So various calculations don't leak over into next steps. Any questions about what one step training loop looks like? Okay. Yeah, and so this is what we were talking about earlier about batches. Is oftentimes you don't just want to pass in one input at a time, you want to pass many because you want to take advantage of GPU's ability to do things in parallel. And so, however, additionally, we can't pass everything in because oftentimes, we have to store all of the intermediate computations and we have to keep the gradients, and that takes up a lot of space in GPU memory. GPU memory is usually about 4 to 80 gigabytes. And so especially once you get into like, well, image processing especially, but also like if you're doing language models and working with like billion parameter models, you'll run into this limit very quickly. And so you then you can only effectively pass in much smaller amounts of this. My advice is generally just pass in or make your batch size as large as possible, such that you won't run out of memory on the GPU. The caveat is if your ability to load data is very slow, you might need to decrease the batch sizes and then to do computations and loading in parallel. But if loading the data and processing it is pretty fast, just try and max out the batch size as much as possible. And then we repeat this process. So we have some of the epochs, and this is really up to you to decide. There's no hard and fast rules for how many epochs. Generally, you'll want to be monitoring your loss and seeing how it's decreasing, and if it seems to plateau and stop decreasing, then maybe take a time to stop. And then we just loop through the entire data set over and over again for as many epochs as you want. Okay, I'm going to talk briefly. How much time do we have? Okay, we got some time. Yeah. So I guess actually first, any questions about that? It's kind of a lot thrown at you if you've never seen training loop before. So Inference, I don't have much to say about this here because Inference is very, very, very problem specific. So for many tasks, it's going to be almost identical to just computing the forward pass. There are some certain modules and layers that work slightly differently during inference, such as dropout. I think batch norm also. However, you also have some tasks that was just completely different than training. So a couple of like mainstream examples are natural language generation, so like ChatGPT. The way that was trained is very different from how you actually run inference and actually generate text. And then also like image generation and fusion. The way you generate new images is very different than how you actually train models. And so sometimes you actually have to write two different functions, one for training and then one for inference. But it really depends on the specific problem you're working with.
Yeah.
Okay.
So what's next in terms of our data? So this lecture, we learned about the data loader class and the dataset class. I also learned about some very basic like transformation, normalization. In the next lecture, we'll be talking about how we can sort of manage different modalities, how we can manage images, audio, and language. So we'll have a Torch vision library for vision, for like, images. We'll also be talking about audio and language processing and how we can do those with Python. And finally, we'll be talking about advanced strategies and optimizations with data loader. So if you guys remember, I only talked about like 4 or 5 like constructor parameters in data loader, but there were like other ones like num workers or like pin memory and stuff like that that I just did not talk about. But oftentimes they're super important for getting high performance. So we'll be talking about that in the next section.
Yeah, and then the couple of weeks after that, we're going to be going more into actual modeling and actually creating your models. So we're going to discuss creating custom modules, and then some of the other things that go into models, such as weight initialization, some of the other common base implementations provided by PyTorch, and some other just techniques to prevent overfitting and some of the things you can add to the model to prevent that. And then the week after that, we're going to be going into just the training loop very much in depth. So we're going to talk about specific optimizers other than gradient descent that you can use. We're going to be talking about how you actually choose some of the hyperparameters, and some of the intuitions and ideas there, such as the learning rate, the number of epochs, how big the model should be, things like that. And we're also going to talk about PyTorch Lightning, which is a library that's very useful for reducing boilerplate. Because a lot of like the training loop that we showed here is almost certainly going to be the training loop you use almost like line for line for many of your projects. And so oftentimes you can get away with using PyTorch Lightning to just reduce a lot of that boilerplate. And it also has a lot of built-in functionality that just makes your life easy. I believe that is it. I think Shirley ends there. In the last 3 minutes, if anyone has any questions, maybe about installing PyTorch on your own machine or anything like that, or you want something to for Shreyas to look at that, let us know.
And also one other thing, I think, did you have a piece of paper? It would be nice if everyone put their names down.
I do not.
Do you create like a Google Sheet or I can probably create a Google Sheet for you guys.
Also, feel free in the future if you ever need help setting up an environment or installing PyTorch, either locally or, you know, if you're trying to get set up on some sort of one of Stanford's like computer clusters, feel free to reach out either in Slack or shoot me an email. I'm happy to help.
Where's yeah, and also for the last time too. So far we haven't done anything, but so far we'll be giving you the recording and the notes actually associated with both.
So when there is a training group, we are not calling inference and comparing what the module gets. Like we're not maybe a different loss function as you said, and maybe like sometimes we have a different inference and different.
Yeah. So if you go to the, I didn't think we'd have time for this, but in the collab at the very end, there's an example of training an entire model. And in there, what I did is I defined a train step and defined an eval step. And so what this loop now looks like is you have 4 team-rich epochs, and then you have the equal train and the equal eval, and the evaluation is slightly different. Because the tasks that I did there was image classification, and so for training, you output kind of just like a probability of what the image is. And then for inference, you actually just choose the maximum value and then you compute accuracy. So it's a different metric. But yeah, I think walking through the example in the collab, I think is probably useful if you understand all the steps there. It's well commented. So.
Yeah, I don't think the dataset examples are in the collab, but I'll put that in the next one with like entire data pipeline, which is really like that.
All right, thank you everyone for coming.
Thanks, guys.